In this video, we're going to look at graphing quadratics. Now that you've already done them using vertex form, standard form, and intercept form, we're going to also include all x-intercepts, not just if it's an intercept form. Now, if we're going to graph a quadratic, you need to be able to find the vertex always, that's that most important turning point, max or min value, the axis of symmetry, which is that vertical line that goes through your vertex. You should be able to find the y-intercept, a symmetric point based off the y-intercept. You can find any symmetric point along the way as well. And then x-intercepts. Sometimes there's one, sometimes there's two, sometimes there's none. In addition to these key pieces of information, you should also be able to check, does it open, up, or down? Is there a stretch or a shrink? Specifically, we will look at vertical stretches and shrinks. You should be able to do transformations. Be able to find that max or min point. And lastly, you should be able to tell your domain and range. So based on those graphs, you should be able to tell everything on the right-hand side here. Now, the questioning part is this x-intercepts. Are there x-intercepts? If so, how do I know, and how many are there? So let's think about what an x-intercept actually represents. If we're looking at standard form, y equals ax squared plus bx plus c. If I want to know if there are any x-intercepts occur when y is 0. So substitute 0 in there for y, and we get ax squared plus bx plus c equals 0. I have a quadratic on the right-hand side, which means if I wanted to solve this to figure out what my x values are, since it's equal to 0, which it has to be, I can either factor or do the quadratic formula. Those are my two options to figure out whether or not we can actually do this. So factor or quadratic formula. And that will tell you what kind of x-intercepts you have. Zeros in there. If possible, I recommend factoring. Again, as we talked about, how do we solve quadratics, cubics, fourths, degrees, etc. We're usually going to set them equal to 0 and try to factor them if possible. Otherwise, we have the quadratic formula, only works for quadratics, and less such effort is putting it into our calculator. Keep in mind your quadratic formula solves for x. The quadratic formula solves for x when it equals 0. 0 equals ax squared plus bx plus c. And my equation then is x equals the opposite of b, plus and minus the square root of b squared minus 4ac all over 2a. Be cautious with the part that's underneath the radical, the b squared minus 4ac. Don't go straight to your calculator. Think about what b squared is. If it's a negative squared is going to be a positive. Don't make any assumptions along the way. So let's take a look at a graph. We're going to graph something that's in standard form. Just like you've done already, we're going to find our vertex, we're going to find our y-intercept, we're going to find a symmetric point. We're also going to find our x-intercepts now. So we are going to graph y equals x squared minus 4x minus 5. So this is the equation we're going to look at graphing. So I instantly know a couple of pieces of information. In addition to that, I'm going to find and look for my x-intercepts. So take a moment, why don't you pause this, graph this the way we did, the way you've done it in the past, looking at your y-intercept, your vertex, and then the symmetric point. So finding your vertex, since it's in standard form, it's the opposite of b over 2a. The opposite of b over 2a in this case gives me positive 4 over 2 times 1. So my x value of my vertex is 2. Substitute the 2 back in for each of your x values. Do the multiplication, subtraction, and you get negative 9 for your vertex. So my vertex is 2, negative 9. Finding my y-intercept. Keep in mind your y-intercept is the easiest. Y-intercept occurs when x is 0. So this is 0 and this is 0. So 0 minus 5 gives you the negative 5. So So I'm going to plot those 2 points quickly. 2, -9. And my y-intercept is 0, -5. Now I know I have an axis of symmetry that runs through that vertex. So over that axis of symmetry, you have that symmetric point. That y-intercept is 2 units away, so therefore I go another 2 units away, and there is my symmetric point. And that's going to be then at 4, -5. Some of you are able to see it without having to go through that process because we're doing the symmetric point off of our y-intercept. The last part then is finding my x-intercepts. So if I want to find my x-intercepts, this is taking just a little bit of space here. To find your x-intercept, or intercepts, we plug 0 in for y. So I get 0 equals x squared minus 4x minus 5. So I have to figure out where does that quantity equal 0. If possible, try to factor it. Product a times c is -5. Sum is your b value, -4. The two numbers that work are going to be a -5 and a +1. Since my leading coefficient is 1, I can shortcut this and say x minus 5 times x plus 1 equals 0. Now if you look at it, it's actually an intercept form besides the 0 equals piece. It instantly tells you your intercepts, your x-intercepts. So set each of those individual x-intercepts equal to 0. Therefore, one intercept is at 5, 0, and my other x-intercept is at -1, 0. It factored nicely, which means they are rational zeros. So now I'm going to go up here and plot 5, 0, and also plot -1, 0. Connect those dots. Will make you a nice parabola shape. This is a nice problem because it factored. You have those rational zeros. That's not always the case though. Sometimes you may not have any. Sometimes you may have just one. Other times they're going to be irrational. So you don't want to have to continue to go through the process trying to see if you can factor if you truly can't. So we have what's called the discriminant test to help us test this out. Now the discriminant test is going to distinguish between the 3 different cases. So let me show you the 3 different situations we could have. One case crosses twice. 2 x-intercepts. In one case, it crosses once, which means it just touches it. The vertex sits on there. And again, it could be upside down as well, opening down. This is going to have 1 x-intercept. And then lastly, could sit above and open up, or sit below the vertex it is. Or have the vertex sit below and open down, and this would have 0 x-intercepts. So these are our 2 different cases that you're going to look at, and we're going to use the discriminant test to determine which of these cases it is. And then we'd have a distinguishing factor on the 2 x-intercepts, whether they're rational or irrational. How can we determine that difference also? So the discriminant test goes as follows. Let's think about the quadratic formula for a minute. This is testing quadratic, so y equals ax squared plus bx plus c. And the quadratic formula is x equals, because we put 0 in for y, so I'll change that to 0 equals instead of y. So x equals the opposite of b, plus and minus the square root b squared minus 4ac all over 2a. We have this limiting factor. I have the square root of something, that b squared minus 4ac. The b squared minus 4ac is my control piece, and that is actually what we call the discriminant. The discriminant itself, if I ever have you calculate the discriminant, it's b squared minus 4ac. And it tells us a lot about our problem, whether we can factor it and how many intercepts there's going to be. Now let's think about this for a moment. There are 3 different cases that we will look at, one a little bit more specific. The first case, if that discriminant b squared minus 4ac is less than 0, so it's negative. B squared minus 4ac is negative. So something underneath this radical here is negative. So then I end up taking the square root of a negative. That's not possible in terms of real numbers. So there are no x-intercepts then. 0. The vertex is going to sit above and it's going to open up, or the vertex is going to sit below the x-axis and it's going to open down. Case number 2 is when b squared minus 4ac equals 0. So now this quantity here is 0. So x equals the opposite of b plus and minus 0 over 2a. So it's the opposite of b plus 0, which is the opposite of b divided by 2a. And it's the opposite of b minus 0, which is the opposite of b over 2a. It gives you the same value twice. If that's the case, there is one x-intercept. And then the last case, which we're going to look at 2 specific ones, is the last scenario, b squared minus 4ac is greater than 0. If it's greater than 0, there's going to be a number that's under the radical. Say it's 8. So opposite of b plus or minus 8, or root 8, sorry, because there's a radical there, over 2a. So I'm going to get the opposite of b plus the square root of 8 over 2a, and the opposite of b minus the square root of 8 over 2a. 2 distinct solutions, which means in that case there are 2 x-intercepts. Now just because there are 2 x-intercepts doesn't mean it's going to be factorable. If there are 2 x-intercepts, there will be 2 different cases that we will look at. Underneath this case where my discriminant is greater than 0, we can have, first case, it could be a perfect square. So for instance, -5 plus and minus root 4 over 2. So the discriminant could be 4. If that's the case, you will then be able to factor your quadratic. And there will be 2 real, rational roots, which are also called x-intercepts. They are rational. However, if b squared minus 4ac is not a perfect square, so say it's 5, so it'd be -5 plus or minus the square root of 5 over 2. If that's the case, then it's going to be a so this is a non-perfect square. And you are going to have to do the quadratic formula. And in this case, you're going to get 2 real, they're still real, but they're going to be irrational roots, also known as x-intercepts. So those are the 3 different types of discriminants you can have, and then whether or not or how you figure them out. If you can factor them, go through that process. It's definitely a little bit quicker along the way. If you can't factor it, if it's not a perfect square, you are going to have to go in to do the quadratic formula. So let's look at graphing the following example just by looking at the discriminant. So y equals that x squared minus 4x minus 5. Let's check the discriminant. So practicing this. So my a value is 1, my b value is -4, and my c value is -5. So my discriminant is b squared minus 4ac. So b squared, -4 squared, so that's 16, minus 4 times 1 times -5, which gives me 16 plus 20, which is 36. Because my discriminant is 36, I therefore know that I have 2 real rational roots, and if I need to figure out what these are to graph it, I am just going to factor it. So one of the nice things about going through the problems is instead of trying to go through, can I factor this, can't I, and try to do some guess and check work with it, you can check your discriminant quickly. If you can't factor it, it's going to be part of the process anyways, and then you'll end up having or knowing whether or not it's factorable. The last part here, so this was all graphing, trying to figure out what kind of intercepts am I going to have, how do I solve for them. The last thing that the discriminant is going to help us do is it's going to help us solve. We went through and we solved by factoring. And then you had a whole sheet on factor this and now solve it, set it equal to 0 and go through that process. But all of that sheet, you could factor them. But what if you couldn't factor it? Or how do I figure out if I can factor it or not? So let's go back really quickly to these rules for graphing and what kind of intercepts we're going to have for graphing. And now let's take a look at what does this look like if I'm just solving an equation. You're still going to do your discriminant test. So let's go back to step 1. B squared minus 4ac is less than 0, means there are no x-intercepts. What that means if we were just solving an equation where it's 0 equals ax squared plus bx plus c, and I was trying to figure out what x equaled, there would be no real solutions to this case. There will be imaginaries, and we'll take a look at imaginaries in the next video. But there's no real solutions for this case. If b squared minus 4ac equals 0, if that discriminant is 0, there is one x-intercept. And what that means for solving, there is going to be one double root or double solution. You have to think about it if we're talking about solutions. And then lastly, if it's positive, if it's greater than 0, we have these two cases again. In part A, if it's a perfect square, there are going to be two real rational solutions. And if it's a non-perfect square, there's going to be two real irrational solutions. They're completely similar due to the fact that when I'm finding my intercepts, I'm always plugging 0 in for y. The same thing's working if you're trying to solve for a quadratic, going through the process. If it is a positive number, like step 3 here, if this is a positive number, if it's a perfect square, you can factor it to solve it. So a little bit quicker to factor it and then solve it. If it's a non-perfect square, as in part B, you're going to have to do the quadratic formula. And then the above ones too, if there's a double root, you can factor it as well. You're going to get a double factor. And then in number 1, if it's no solution, we're going to have to start working with i's, which we'll do later on. Now let's just do a couple of examples here so that you can see what this looks like in the process. So we are going to solve 3x squared minus 17x minus 28 equals 0. So if I want to solve this problem, I need to either do the quadratic formula or factor it. I'm trying to cut down on as much work as I can. I look at that and I'm going, okay, my product is 3 times negative 28 and my sum is negative 17. I don't know right off the bat if that's factorable or not. So what you may want to do is calculate your discriminant, b squared minus 4ac. So it's negative 17 squared minus 4 times 3 times negative 28. One quick thing to notice is it's a minus 4, and then there's this negative in here, which is going to make it a plus, so it's going to be a positive number. So 625. So I know I'm going to get real solutions, and 625 is a perfect square, therefore I can factor it. So now I'm going to go through that work of doing the product and sum to factor it to give you the practice as well on this. So my product is 8 times c, so 3 times negative 28, which is negative 84. And my sum is b, which is negative 17. So going through how we actually factor, what two numbers multiply together give you negative 84, add together to give you negative 17, gives you 4, and negative 21. So now I'm going to split up that middle term. It's 3x squared minus 21x plus 4x minus 28 equals 0. Group the first two, group the last two. Factor out what's common. Factor out a 3x, and you're left with x minus 7, plus factor out a 4, and you're left with x minus 7. This all again equals 0. So since they both are attached to the same thing, which has to happen when you split the middle term, it's 3x plus 4 times x minus 7 equals 0. So now set each of those individual factors equal to 0. Therefore, x equals negative 4/3 and positive 7. Of course, after you solve for this, you should check it as well, plugging it back in. Yes, they do both work. Therefore, my solution is containing the values of negative 4/3 and 7. Doesn't matter which order you go. So this is a solving quadratics that works by factoring. Because my discriminant was a perfect square, I could factor it. Next one. Solve 5x squared plus 4x minus 4 equals 0. Numbers are a little bit smaller along the way, so it might be a little bit easier to do a bit of guess and check with it. My leading coefficient isn't 1, so it's a little bit more difficult. So do your discriminant. Take a second, do that. B squared minus 4ac. Your discriminant's 96. Not a perfect square. Therefore, I have to do the quadratic formula. So x equals the opposite of b, plus and minus the square root of b squared minus 4ac. That's your discriminant. You already did that part of the work. All over 2 times 5. That's the bonus of finding your discriminant ahead of time, is if you do the quadratic formula, you actually do the hard part right away from the beginning. Now I have to break down my radical. Everything's going to be exact unless I were to physically be graphing this, but I'm not. I'm just solving for x. So I break this apart. Perfect square is 16, and what's left over is 6. So it's 4 root 6. Plug that back in. Negative 4 plus or minus 4 root 6 over 10. Think ahead, pull out what you need to. What do they both have in common? The numerator you can factor out a 2. So factoring out a 2, I'm left with negative 2 plus and minus 2 root 6 over 10. So 2 goes into 2 once, 2 goes into 10 5 times. So it's negative 2 plus and minus 2 root 6 all over 5. Because my discriminant was not a perfect square, I had to go through and do the quadratic formula. Last problem. Solve x squared plus 10 equals negative 2x. In order to solve this, I have to have it set equal to 0 because there's an x and an x squared both in here with a constant. So add that 2x over x squared plus 2x plus 10 equals 0. Doing my discriminant test, b squared minus 4ac. 4 minus 4 times 1 times 10. Hopefully you see that's going to give you a negative. It's a negative 36, which is actually nice, and we'll work on those with imaginaries. But because that's an imaginary, or because that's a negative, there are no real solutions. So what you would say at this point is no real solutions. This is the last time you're actually going to write that, first and last, I guess, because we're going to start working with imaginaries, and we are going to actually find imaginary solutions, which we'll work through and talk about later.